Hello, welcome to video 55 in the lecture Advanced Mathematic Modeling. So now after we've discussed in detail the properties of fractals, these were geometric objects where some properties change as a power law with scale. I want now to look a bit more general and maybe a bit more simpler systems. What do we mean in general by scaling? So how do properties of objects change with scale, and what does this mean for geometry and of animals or buildings and so on? So let's have a look. So in many objects the properties scale as a power law or change as a power law with the scale. So if you have a property x and a scale s, very often, for many cases, we see that the properties of an object go with the scale to an exponent alpha. So we have here power law. Now this is not a power law distribution in this case. We are not speaking about a distribution of probabilities, just as properties of objects depending on the size. So where do these power laws come from? And this often the reason is often just simple geometry. And here I don't mean fractal geometry, I mean more simple geometry. Because, so let's say, what is the volume of an object, a volume of an animal or whatever? So the volume very often scales with the size of the object to power 3. And so how is this with a let me see which order I wanted to do this. So okay, the volume goes very often with the size to 3, and if we have a surface, the surface of many objects scales with the size to power of 2. Here, let's say the surface of a sphere, the surface of a cube, and so on. This goes with the size to power 2. Now you can think, so what properties are associated to volume? Yeah? So to the volume, so the weight of an object. The weight of an object increases with the volume, assuming constant density. Also, if we want to carry something, the capacity, if you have a bag or a car or something, a ship, the capacity scales with the volume. Or very often the costs to build something, in the simplest case, just scale with the volume. Yeah? So there's many properties which scale as a volume, and these are properties which scale with this, the size of an object to power 3. Now there's other properties which depend on the surface, and very often these are properties which depend on transport processes to the interface of the object to the rest of the world. For example, input fluxes, or heat radiation. So I mean, if you have an object and you want to know how much transport, you have an oven, you want to know how much heat can be going out of the oven, then it depends on the surface of the oven, not on the volume. You have a phytoplankton cell and you want to know how much nutrients can be taken up by the phytoplankton cell, then it depends on the surface because of the number of uptake proteins you can have on the surface. These are properties which go with the surface, not the volume. Here, often something like a friction of objects, they depend on the surface. Yeah? And of course, this is now very simple reasoning. I mean, of course, not only the volume and surface, but also the shape and many other details go in, how really the weight or the capacity of an object, how they will change, what will be the exact value. But if you want to know in general how such properties change when you just change the size of an object, then typically here we have for these certain properties, they have a power law with exponent 3, and other objects which have power law with exponent 2. And now you can see relate these things. For example, now you can see the volume goes then proportional to the surface to 3/2 if you just plug one in the other. Or if you have a ratio of surface to volume, surface to volume ratio, then this scales with one of the size of an object. This means the larger an object, the less important is the surface in comparison to the volume. And now, so this means now if we now look for certain objects of different sizes, this has immediately consequences. But before I discuss some examples, let's again in general have two power laws. And we have a double logarithmic plot. Here we log size, and here we have the log of some property. And let's say we have a power law, and our property scales with the power law, and we have a certain exponent. So on a double logarithmic plot we have a straight line. And now that was the property x, and now we have another property which goes with a different exponent. That's the property y. For example, this is the volume and this is the surface. And if we now have two different properties which scale with different exponents, then you see we have here a regime where the dominance of one of the power laws is changed. So here in this regime of small scales, we see that y dominates. So example, if this would be volume and surface, then for small scale the surface would dominate. But then for large scales, x dominates. And this might look not so big, the difference, but we have a log scale, so this is really can be factor of 10 or 100, or here also. Yeah? So we see a transition from small-sized objects will be dominated by property y, and large-scaled objects, large-size objects, will be dominated by y. And then we have transitions. So now let's look at examples of all of this. And before I forget this, I think I recommended this already, this book by West, this book Scale. This has many different very well described examples of this. So let's take, for example, heating of a house. Then you could say the amount of energy you need for the heating. This goes with the volume, but the heat radiation goes with the surface. Then it means the efficiency of the heating decays with the volume. Because the efficiency has something to do with the surface to volume ratio, and for large volumes the surface to volume ratio decays, and this means when you have a heating which is very big oven, this will not be as efficient. Now translate this to animals. If you have an animal, it needs also to have animals produce body heat, and they have to get rid of the heat, especially if they're in a warm place. And then this means big animals are not as efficient to get rid of heat. Now take a hot place. You're somewhere in Africa, and you have a small mammal, a small mouse, and an elephant. And so the mouse has a very rather large surface to volume area, has a large surface, and has not so much problems to get rid of the body heat, whereas the elephant has a lot of problems to get rid of the body heat. And so what was the answer from evolution, from nature, to help the elephants? So the elephants have these very big ears, and have big ears, and the big ears are just there to help elephants to get rid, so like a heat radiators to help elephants to get rid of the body heat. Yeah? So you see, such a scaling or such a surface to volume ratio in an animal has immediately consequences for some physiological functions, and this determines how anatomy of animals changes with the body size. And this is so important. This became part of biology, where one looks how body functions and physiological functions scale with body size of animals. Take now here capacity, take shipping. Other examples. So if you have a ship, then the capacity goes with the volume, but the fuel goes roughly with the cross section of a ship. And this means if you can, now you take the ratio, so then we need the volume to surface or cross-section ratio. If this is larger, then for the same fuel we get much more capacity transported. And that's the reason why cargo ships get bigger and bigger and bigger, because then for the same amount of money, and a lot of money in shipping goes for the fuel, you get more cargo transported. Cargo ships get bigger and bigger. And this goes to really extremes, like the modern new cargo ships have incredible sizes, which need very special ports in order that the ships even can go to the ports. You might know that close to Oldenburg here in Wilhelmshaven we have now this new port, which is a deep water port where these big cargo ships can really enter, whereas in ports like Hamburg, where you have big rivers and you have to go ship along the Elbe River, such big cargo ships have problems. And why do these cargo ships get larger and larger? This is just a consequence of simple scaling. Now let's look another thing. Let's look at scaling of buildings or static. So, and let's say if we have a beam, so like here we have so it's a beam that we want to use for construction. Because we want to build a house or bridge, and then we have here this cross section area, and then the strength. So how much physical force can be taken up by such a beam goes proportional to this cross section A. Now what does this mean? So now what does this mean when we want to calculate the maximal load? Of the beam? Then, I mean, so we said before, the strength that can be taken up depends on the cross section, but the weight of a building goes with the volume. Yeah? So the strength goes proportional here again to the cross section, which goes with S squared, and the weight, so which gives the physical force, goes with the volume, and this goes with the size to power 3. And this means if we increase the size of such an object, increase the size of a building, which could be here a bridge or a house or something, then the weight, the force from weight, increases faster, than the strength. So we get here again this transition between small and large objects, where either the thing is dominated by the force of the weight or the strength of the construction. And this means that if you have a building, let's say you have here a small house, and if this is statically okay, this would be stable. If you now to scale the same house, just make it a bit bigger and make everything isometrically bigger, yeah, and then you make the same house again and make everything bigger and bigger and bigger, if you take such an isometrical scaling, which means all ratios in the house, all proportions stay the same, and we just make a bigger version of the house, from a certain point this will be unstable and will break together. From a certain point the house will break together. Yeah? Or for your bridge or whatever. And what does it mean? In practice, the bigger house, like if this here is the size of the beam or the wall, the size of the wall, and now the larger house needs an over proportional bigger wall in order to sustain the weight. Yeah? So if you just would isometrically scale the whole thing, it would break apart. Now this was for bridges and houses, but the same holds not only for beam, but holds also for bones and animals. And now if you take a small animal, then the small animal has an over proportional strong size for its weight. The small animals are relatively strong in terms of their body size. So you know an ant can carry a multiple of its own body weight here. But if you look again at the elephant, yes, our biggest mammal, so it needs very thick legs in order to carry the weight. Very big legs. Same as a big house or big building needs very big beams. And this goes this observation goes back to Galileo. In old days, who found this law already, that small animals are stronger than big animals. And this book by West, he gives a nice example where he was asked for a movie, for this Godzilla movies, where you have this King Kong, where you have this super duper big sized animals. And then he said, yeah, but these animals should look different, because like the King Kong is just a scaled up version of a small monkey or a gorilla. And if you would scale up the gorilla to a very large gorilla, it would just break apart. It couldn't hold his body weight. So actually a King Kong would need much thicker legs than it has in the movies. So a King Kong would break under its own body weight. And so when you look at this, again, simple scaling of volume and surface tells you something about the static properties of objects of different scales. It tells you something about animal physiology, how the body form of animals or of buildings. Now the thing is, can we test this and practice if this is really true? How can we test this? And this was an idea which goes back to Lietzke. And he looked at Olympic Games. In 1956, and he looked at the records of weightlifting. And why would you do this? Because you want to know what is the strength of a human as a function of body size. So, but how can you measure the strength of a human? And Lietzke had the idea, oh, we don't need to measure this. I don't need to pay students to make all kinds of performances for me. I just take the records from the Olympic Games. I take the best people in the world. And weightlifting is very cool because I get a number. I see what is the weight a human could carry, and then we plot here a log of the strength, and I get the strength in the kilograms that the person was able to lift. And here we can make a log of the body weight. Of the persons. And so that's also nice, the body weight, because in weightlifting, and that's there's different weight categories. So we have these different weight classes, and then you have here maybe the 55 kilogram people, and then you have the 61 and so on. And here somewhere you have the 102 kilogram weight class. So we have the different weight classes, and it's clear that there are the more individuals who are bigger, who have more weight, can carry also higher weights, are stronger, and smaller people are not so strong. And now, so from the Olympic records, we get then for every weight class, we get the weight the people could lift. And for you now in this lecture, it will come at no surprise that this falls in the power law. And so what is the slope of the power law? So what would we guess? So we would guess that this would depend on here s squared by body weight. So we would expect an exponent of 2/3, and here the fit gave a number of 0.675, which is good enough, equals to 2/3. So really the weight a person was able to lift at the Olympic records was proportional to the body weight. So the strength was proportional to body weight by a power law of an exponent 2/3. Strength of human was proportional to body weight to 2/3. And that's now interesting to see, I mean, which of the individuals we had here, of the people who were taking part of the gold medal winners, was the most strongest. And actually it was interesting that in some middleweight, here there was a point actually which was a bit higher above the here the regression line, whereas the super and the biggest weight class, actually the point was a little bit below the regression line. And then you could say, okay, this guy here actually, relatively to his body size, was the most the strongest, the relatively strongest person of all the people, because according to the scaling law, for his body size he was relatively stronger than this guy, even though in absolute numbers this guy could lift more weight, but according to his body's weight he should have been able to be a bit more strong. So these were just some very simple, naive scaling arguments which just depend on surface and volume, and so these are calculations you can really do as on an envelope. It's very hand waving, all these discussions, but you saw we can with this explain why elephants have big ears, why container ships get bigger and bigger, why big animals have big legs, why small elements are so strong, why big buildings need relatively bigger beams, and why and in which form the strength of humans depends on body weight. Yeah? Even so there was no intricate math behind this. You just see that also for all these properties, power laws are the fundamental properties or the fundamental construct to understand this. And now in the but these were just simple cases of such scaling, and in the next video we want to look at some more interesting scalings which are not so trivial as these. But for the moment,